Good evening, class 11. Let's start. Today we are going to start ionic equilibrium, Oswald's dilution law. According to Arrhenius' theory of ionization, there is dynamic equilibrium between the ions of an electrolyte in solution and the undissociated electrolyte molecule. Now we need to remember this is basically for the weak electrolyte, because strong electrolytes undergoes complete dissociation, right? But weak electrolyte undergoes partial dissociation, right? So some ions are formed and some remains in the form of undissociated molecules. So this is basically applied for the weak electrolyte. If I take my electrolyte as AB, reversible, A positive, B negative. If this is my strong electrolyte, this entire molecule will be splitting into ions. So nothing will be remaining as the molecule, right? But if this is a weak electrolyte, then only some will remain in the form of this undissociated molecule AB and some will be dissociating into respective ions. So this is applicable only in case of the weak electrolyte. Now we are taking that initial concentration of the reactant is C moles per liter. Initial is C moles per liter, and initial means you have just started the reaction, so products form 0. Equilibrium concentration of this one, equilibrium concentration. Now if I suppose that alpha is the degree of dissociation of AB at equilibrium, right? If alpha is my degree of dissociation at equilibrium, then C minus C alpha, and this one will be formed as C alpha. Alpha being the degree of dissociation means what? From C your alpha percentage gets dissociated, right? So C alpha are the moles of the products and C minus C alpha is the moles of the reactant, right? Now applying the law of chemical equilibrium, I can write K. It's an equilibrium constant. It is your this one. It is a ratio of concentration of the products to reactants. So this one will be my C square alpha square by C1 minus alpha. So C will get cancelled. So C alpha square divided by 1 minus alpha. Now for a weak electrolyte, this alpha is very small. So I can take this 1 minus alpha term, approx equals to 1. We can ignore this alpha value. So this one is equals to, means K is equals to your C alpha square. Or I can write alpha equals to root over of K by C, where K is a constant. It is the K is basically the dissociation constant and C is the concentration, okay, in moles per liter. Now if your weak acid is involved, then this K is represented as Ka for weak acids. If weak base is involved, then this K is represented as Kb. Okay. Now the importance of Oswald's dilution law, it is applicable to weak electrolytes only and is very useful in the calculation of the dissociation constant of weak acids and weak base from degree of dissociation, right? So it is it is applied only for the weak electrolytes. Now next we move to concepts of acids and bases. Under concepts of acid and bases, we have Arrhenius concept, Bronsted-Lowry concept, and then we have Levy's acid-base concepts. According to Arrhenius concept, acids are the substances which produces hydronium ions in aqueous solution, and bases are the substances that produces hydroxyl ion in aqueous solution, right? So according to Arrhenius concept, your HCl is an acid, H2SO4 is an acid, HCN is an acid, and which are bases? Definitely the ones containing hydroxyl ions, that is NaOH, KOH, calcium hydroxide, etc. Okay, next we move to, yes, one more thing. In case of Arrhenius concepts of acid and base, acid-base neutralization will be producing what? Salt and water. Okay, next we move to Bronsted-Lowry concept. According to Bronsted concept, acids are substances which are H plus donor or proton donors, and bases are substances which are proton acceptors. So according to Bronsted concept, HCl is an acid, H2SO4 is also an acid. Even water is also considered as an acid depending on the nature of the solvent. In case of Bronsted concept, acid-base neutralization leads to the formation of conjugate acid-base pairs. For example, if I take HCl and H2O, here definitely HCl is an acid and water is a base. So acid is what? It is proton donor. So it will be donating H positive to whom? To H3, to H2O, forming hydronium ion and Cl negative. So this is my acid and base. Now if I consider the backward reaction, then this one will be what? These are the conjugates, out of which one will be conjugate acid, other one will be the conjugate base. So hydronium will be conjugate acid and Cl negative will be the conjugate base. Why this is the conjugate acid? Because if I consider the backward reaction, then hydronium ion will be donating H positive to Cl minus. So it is conjugate acid and this one is conjugate base. If I take a reaction where water is only used as a solvent, but another one we have ammonia. Previously we were using HCl, here we are using ammonia. Ammonia, it's a strong base, so definitely water in presence of ammonia will be acting as a acid. So ammonia will be accepting proton from water and hydroxyl ion will be formed. Okay. Next we have Levy's concepts of acid and base. According to Levy's concept, acids are electron pair acceptors and your bases are electron pair donors. Now according to this Levy's concept, we have four classifications, four types of Levy's acids we have. First type, molecules in which the central atom has incomplete octet. For example, if I talk about BF3, AlCl3, the central atom has incomplete octet, so they can act as Levy's acid. Next, simple cations like H positive or even some transition metal ions like Fe3 positive, Cu2 positive, which due to the presence of vacant or partially filled orbitals can act as Levy's acids. Next, molecules where the central atom has complete octet but can act as Levy's acid due to the presence of vacant d orbitals. Example, SiF4. Your octet is complete but silicon vacant d orbital is present, 3d orbital, so it can behave as a Levy's acid. And molecules where multiple bonds are present, that is CO2, SO2, etc. They also can act as Levy's acids. And Levy's bases, we have neutral molecules like NH3, primary amines like RNH2, these are the amines, water, these are the neutral molecules, and anionic, like we have all halides, hydroxide, etc. Okay, now in case of Levy's concept, acid-base neutralization will result in the formation of coordinate bonds. I'll be showing you by an example. Copper ion Cu2 positive, it's a Levy's acid. Ammonia is a Levy's base. What will be formed? This one, via coordinate bond. So ammonia is donating its lone pair to copper. So coordinate bonds are formed. This is my Levy's acid base adduct, which is highly stable. Okay, so that's it, class 11. Thank you.